Hi students, welcome back to Physics for All YouTube channel. In this session, I'm going to start the second unit, which is known as Crystallography and X-ray diffraction. This syllabus is related to the JNTU Anantapuram and Kakinada University and some topics also related to the JNTU Hyderabad. Watch these slides carefully in order to understand about the fundamentals of crystallography as well as X-ray diffraction. This is the syllabus of the crystallography, which contains introduction about crystallography, space lattice, basis, unit cell, and lattice parameters. Then Bravais lattices, crystal systems, coordination number, packing fraction of simple cubic structure, body-centered cubic structure, face-centered cubic structure, followed by Miller indices and derivation of equation between successive HKL lattice planes. After this crystallography chapter, we'll discuss about X-ray diffraction, introduction, X-ray diffractometer, crystal structure determination by using Lye method and Porter method. These are the two chapters included in the Unit 2 of Engineering Physics syllabus. Now we'll discuss one by one in this crystallography. Now, first of all, depending on the arrangement of atoms, matter is classified into three categories. They are known as solid state material, liquid state, and liquid crystal materials. And the third one is gaseous material. In the case of solid state material, already everybody knows that solids have fixed shape and size. What is the reason behind this fixed shape and size? The main reason of fixed shape and size of the solids, in the case of solid state material, all atoms are separated at very low distances of the order of few nanometers or angstrom. Because of low interatomic distance between the atoms, these solids atoms are having larger interatomic forces. These larger interatomic forces is a creation of potential energy which bind the atoms together. Because of strong binding energies between the one atom and another atom, these solids are having incompressible nature, rigid in nature, and also mechanically strong. These are the reason behind the solids. Now coming to the liquids as well as the gaseous material, already in the case of liquid material and gaseous material, there exist all atoms which are separated with more interatomic distances. Because of more interatomic distances between the neighboring atoms, they do not have strong bonds. Because of strong bonds between one atom and the other atom, they do not have strong bonds. Because of this reason, they do not have regular shape and size. Now, in this situation, I am going to explain there is a relation between the interatomic separation and interatomic force, that is equal to F is inversely proportional to 1 divided by R. So, because of this reason, if R is equal to low value, there will observe more force. These interatomic forces creates binding energies. These binding energies between the neighboring atoms bind the atoms. Because of this reason, solids are having perfect shape and size, and liquids and gases do not have perfect shape and size, and they possess the shapes of the content. This is about fundamentals of solids, liquids, and gases based on the interatomic distance. Now we'll discuss about, again depending on the distances between the neighboring atoms, we are going to divide two types of solids. Number one is crystalline solids and number two amorphous solids. Now we'll come to the amorphous solid. Now in this diagram, you measure distance between these two atoms and these two atoms. So in this case, distance is more and here distance is less. Or you can observe these two atoms distance is moderate. So if you can observe this diagram carefully, you can take any two atoms on x dimension, y dimension and z dimension. The distances are not uniformly arranged. Because of non-uniform distances between the neighboring atoms, in the case of amorphous solids, these atoms do not have perfect binding between the neighboring atoms. Because of this reason, amorphous solids do not have particular shape and size. This is about the reason why amorphous solids are not having a perfect shape and structure. Now coming to the crystalline solids. In the case of crystalline solids, you can take any two atoms on the x direction or y dimension or z dimension. All atoms are uniformly distributed. Because of uniform arrangement of all atoms inside of this material, crystals are having, or crystalline solids are having, perfect shape and structure. This reason gives the various properties of solids like electrical properties, magnetic properties, and other mechanical properties of crystalline material. Now we'll discuss what are the example for the crystalline solids. Example for crystalline solids are gold, all metals like gold, silver, aluminum, and non-metallic crystals like diamond, silicon, quartz, graphite. These are the example for the crystalline solids. Now coming to the example for the amorphous solids, plastic, rubber, glass, galena, Thor. These are example for the amorphous solids. Now we'll discuss what are the properties of crystals. Because of smaller interatomic separation between the neighboring atoms, small interatomic separation between the neighboring atoms, crystalline solids have sharp melting points. They have long range positional order. Crystals are anisotropic in nature and they exhibit birefringence, and some crystals exhibit piezoelectric effect and ferroelectric effect. These concepts can be discussed in the another chapter like ultrasonics and dielectric materials we can discuss. Now, after the properties of crystalline material, now discuss about the some more fundamentals related to the crystallography. The very first important definition is lattice point, and the second one is space lattice, basis, and Bravais lattice. Now, in order to understand about all these definitions, first of all, we have to understand what is the meaning of crystallography. Crystallography is a branch of physics which deals with the study of various crystals. By observing the various crystalline material nature, these can be very useful in determining the properties of materials like electrical properties, mechanical properties, conducting properties, magnetic properties. So it is very important to us to know about the crystallography. Now, in order to analyze the structure of given material or given crystal, first of all, we have to identify position of atoms. These atoms are in million in number in any material. Therefore, these atoms cannot be identified by the human eye. So, how can we identify the position of atoms? Means atomic locations can be identified by using an imaginary point. This imaginary point is known as a lattice point. With the help of the lattice point, we can able to identify position of the atoms in any given crystalline material. Now coming to the second definition, that is known as space lattice. In the case of space lattice, the summation of all lattice points in a given crystalline material, which is known as space lattice. Now we can get bases. Now basis is nothing but corresponding to each lattice point, there exists one or more number of atoms are associated in that material. Each and every group is known as a basis. Now, if the basis contains identical or uniform environment, such type of lattice is called as Bravais lattice. If the environment does not contain uniform environment, such lattice is called as a non-Bravais lattice. In order to understand about these definitions, now let us consider simple diagram. In this diagram, all the dots represents atoms. All the dots represents atoms. Now our main concept is we have to identify the location of atoms. If atomic locations can be found, then with the help of these atomic locations, we can identify the given material is simple cubic structure or body centered or face centered or base centered. In order to identify all the atoms in a given material, it is necessary to identify the atomic locations. So these atomic locations can be identified by using the reference point. That reference point is called as a lattice point. Now in this two-dimensional example, now corresponding to this lattice point, one atom is associated. Now to understand about this, I am changing the color of the atom. Now this blue color represents atomic locations. Blue color indicates atomic locations and all the red color indicates lattice point. Now to identify the location of atoms in this given material, I am using a reference point. That reference point is called as a lattice point. Now in this example, so go through carefully. Now this is red color indicates a lattice point. So corresponding to this lattice point, one atom is associated. Now corresponding to another lattice point, one more atom is occupied. So lattice points are used to identify the atomic locations of the given material. That is the main purpose of lattice point. After identifying the lattice point, now we can combine all the lattice points, which is known as space lattice. Now we'll come to the definition of basis. Now you can observe this group. This group contains one atom related to the one lattice point. Now you can take this group, or you can take this group. This group also contains one lattice point related to the point one atom associated. These individual groups. Now here, these individual groups are known as bases. These individual groups are called as bases. Okay. Now, if the basis contains, suppose you can take this basis. This basis contains two atoms, whereas this basis contains one atom. Therefore, now compare this basis and this basis. Now compare in second. Now compare this basis and this basis. This basis contains two atoms and this basis contains only one atom. If an environment is not identical, such environment is called as non-Bravais lattice. Suppose if each and every basis contains uniform arrangement of atoms related to the all lattice point, such environment is called as Bravais lattice. Now after these fundamental definitions, now we'll go to the another definitions like unit cell and lattice parameter. Now, in order to study the entire crystal structure, now we have to divide the total crystal structure into smallest parts or smallest blocks. Now, the smallest part, which is repeated along the three dimension, the shape of the smallest block is called as unit cell. If you can identify the shape of the unit cell, then it is very easy to identify the total shape of the given crystalline material. Now, in order to identify the unit cell shape, it is necessary to identify length of the x-axis, length of the y-axis, and length of the z-axis. These lengths are called as A, B, C. A, B, C are called as length of the x-axis, y-axis and z-axis in the unit cell, and angle between x and y is alpha and y and z is beta and zx is gamma. These alpha, beta, gamma and A, B, C, and these two are commonly called as lattice parameter. With the help of the lattice parameter, we can categorize into 7 shapes of the unit cell. Now this can question, now this is a two-dimensional crystal. Here all atoms are uniformly arranged along the x-axis and y-axis. Now this is a periodic arrangement of all atoms. Now depending on the unit cell, now this is depending on the lattice parameters of the unit cell, we can categorize unit cell shapes into 7 shapes. Now these 7 shapes are commonly called as crystal systems. This concept is very important for the essay question in the university end examination. Now depending on the lattice parameter, categorizing into 7 types of unit cell shapes. They are called as cubic crystal system, rhombohedral crystal system, tetragonal crystal system, orthorhombic crystal system, hexagonal crystal system, monoclinic crystal system and triclinic crystal system. In these type crystal systems, the respective dimensions are tabulated in the table. For example, I am going to explain about the only one crystal system which is known as a cubic crystal system. In this cubic crystal system, length of the x-axis and y-axis and z-axis all are equal to each other, that is A is equal to B is equal to C. Now coming to the angle between xy, yz and zx, these three angles are mutually perpendicular to each other. Such a system is called as cubic crystal system. Now coming to the second system is rhombohedral. In the case of rhombohedral, three sides are equal and three angles are not equal to 90 degrees. Now third crystal system is tetragonal. In the case of tetragonal crystal system, any two sides are equal to each other and third length is not equal to each other. Coming to the angles, all angles are mutually perpendicular to each other. Now coming to the orthorhombic crystal system, two length equal to each other and third one is not equal to each other and all the angles are mutually perpendicular to each other. Such system is known as orthorhombic crystal system. Now hexagonal crystal system means two sides are equal to each other and third side is not equal to the first two lengths. Then the coming to the angles point of view, any two angles are mutually perpendicular to each other and the third angle is equal to 120 degrees. Now beside this table, already we are showing diagrams for each and every crystal system. You compare the shape of the crystal system and you observe the diagonal. You understand here. For example, in the case of hexagonal, two sides are equal. Now in this example, this axis and this axis are equal, while the third axis is not at all equal. Now coming to the angles point of view, two angles are at 90 degrees. Coming to the third angle, which is equal to 120 degrees. So such a system is called as hexagonal. Coming to the monoclinic crystal system, all the three sides are not equal to each other. Now in the case of monoclinic, three sides are not in equal length. Now coming to the angles point of view, two angles are mutually perpendicular to each other and the third angle is not equal to 90 degrees. You observe the diagram of monoclinic. And the last one is triclinic crystal system. In this system, all sides are not equal to each other, that is x-axis length, y length and z length, which are represented by A, B, C, all are not at all equal to each other. Now coming to the third angle, coming to the another angles, A alpha is not equal to beta is not equal to gamma is not equal to 90 degrees. Such system is called as a triclinic crystal system. This is about some fundamentals of crystallography. Now in this session, I have explained about, first of all, definitions of lattice point, space lattice, basis, unit cell and lattice parameters, and also based on the dimensions of the unit cell, we divided into 7 types of crystal systems. Just now we discussed about these fundamental concepts in this session. In the upcoming session, I am going to explain about very important concept, that is definition of coordination number, atomic radius, packing fraction, and based on these 3 definitions, we'll discuss about simple cubic structure, body-centered cubic structure, and face-centered cubic structure. For examination point of view, university examination point of view, these questions are very important for university and examination. So all of you who subscribe this channel and like this channel, if you are interested, share this channel to your friends in order to get regular updates. In the upcoming session, we will explain about the simple cubic structure, body centered and face centered. These concepts are very important for the university and examination. Thank you.